Hello everyone. In this video I'll be showing you how to set up a calculation in GaussView. So there's several different ways that we could get to the calculation setup menu. We could go to calculate and then click on it through here. That is the first way. We could also double click on the molecule viewer, go to calculate again, click on it, or finally we could just click Command G. That will also bring it up. So we have many tabs here. First of all, we have the job tab, which allows us to do energy. This just calculates the single point energy of the molecule. We could optimize the geometry of the molecule. This allows us to calculate either the minimum, the ground state energy, or we could calculate a transition state energy. We could also change force constants. Here we could calculate the frequency, we could calculate the Raman spectra, and here we could calculate both the optimized geometry and the frequency. We could do a minimum, we could calculate force constants at either every iteration or just the first one, and we could select if we want the Raman spectra or not. We could also select if we do or do not want the normal modes calculated. Here we could calculate the intrinsic reaction coordinate. We could do forward, backwards, or both, and again calculate the force constants if we'd like. There's also stability. Here we have scan. As we saw in the last video, we need redundant coordinates. We could also calculate NMR. In this video, we'll do an optimization and frequency calculation. We will calculate to the minimum ground state energy. For speediness of the calculation, we'll just do calculate at first point for force constants, and we will neglect the Raman spectra. For the method, we have several options. First of all, we could do either a ground state or other methodologies. We can select whether we want to use semi-empirical, like PM6, which is a very, very low fidelity model. We could select Hartree-Fock, if we'd like. We could also select density functional theory. They provide several functionals, B3-lib, PBE. If you want to select a different one, you could add it in the additional keywords below. We could do Muller-Pleasant perturbation theory. We could do a couple cluster singlet and doublet excitation method, and we could also add triplet and quadruplet excitations. We could also do CBS, QB3, and those higher fidelity models. Here, if we wanted to do, like I said, a different DFT, we could do, for example, MN15 if we wanted. We could do MO6. We could do older methods like Goddard's X3-lib, anything that Gaussian supports, really, which you could find in literature or online. For this video, we'll use PBE. Here we could select the basis set. We could go with Slater type orbitals, or we could go with a larger basis set. The larger basis set, the more accurate the calculation, although the longer it will take. So let's go with 631. We could add polarizable functions and diffuse functions here. So we'll go 631G plus, let's do D and P. We could also change the fitting set if we want, but for now we'll just leave that alone. We could change the charge, and we could also change the spin state. We'll go with singlet for now. Next we go to title. This just allows us to kind of name the calculation. So for now I'll say it's DMA, it's a geometry optimization. Here you select the memory limited and shared processors. Since I'm using a supercomputer, my computer needs 3 gigabytes and allows for 12 shared processors. We could change the checkpoint file, which typically saves things like orbitals. For now, we will not save it. Here we have general options. We could use quadratically convergent and self-consistent field. We could ignore symmetry, which we will do for now. Typically, that'll just lower the calculation time. For population, this allows orbitals. So let's say if we wanted to calculate the NBOs, natural bond orbitals, we would put full level output, we'd put full NBOs and save NBOs. But for quickness of calculations for now, I will just not do orbitals. Finally, we have solvation here. You could use things like solvent model based on density, polarizable continuum model. Since I'm doing DMA, I will use solvent model based on density, and I will try to model the methacrylate environment with acetonitrile. If you want to use a custom solvent, you could just click on the solvent and go down to other and type in the solvent that you want, and I'll try to find the dielectric constant for whichever one you're trying to use. Additionally, we have additional input, which is similar to additional keywords. So again, if I wanted to use a Minnesota functional or something not already allowed. And then here it just gives you a preview. Here it shows the processors, the memory. It gives up the info. So there's a frequency calculation, no Raman, save modes, PBE 631, SMD, modeling acetonitrile, no symmetry, etc. Here's the title. Here we have the charge and the spin state, zero charge, singlet, and here's all the atoms and their Cartesian coordinates in our molecular viewer, as well as the bonds and things like that. If you have a bunch of calculations that use the same calculation setup, you could also retain your current configuration so that you could just simply click on your scheme instead of having to do everything again. And for now, since we're sending it to a supercomputer, we'll edit it. And we'll go ahead and save it. For me, I'm going to put it on the desktop. I'm just going to name it something like DMA, it's a geometry optimization. I like to use the functional, so PBE, and the basis set 631 dp, and then the solvent. Typically, you need to use underscores when you're submitting to a SFTP, just because they don't like it when there's spaces or things like that. And then GaussView will output the input file that you are going to be sending.